Okay, here's a second example of analyzing a circuit with passive circuit elements. Okay, so we start with this circuit that has two resistors, an inductor, and a capacitor with an input voltage source, and the output is across resistor R2. Okay, we'd like to find the transfer function V out over Vin. Okay, so the first thing we do is we take this circuit into the Laplace domain, all right, and so I'm going to apply an impulse function for the input, so that would mean the voltage source now is the Laplace transform of delta t, which is 1, okay? And then resistors in the Laplace domain are still resistors, resistors in the Laplace domain are the same as they are in the time domain. So R1, okay, and then the capacitor becomes 1 over CS. The inductor becomes LS. And as I said, the resistor stays the same. And now we have capital V out. It's actually a function of S. Okay, so our task here is to analyze this circuit using circuit analysis techniques that you learned in a different class. Okay, so one quick way to do this one is with node voltage, and so I'm going to remind you of how to do that. With node voltage, you choose some reference point. So here's the reference point that I'm going to choose, and then we label this, let's call it VA. All right, from there, we do calculations to get the currents coming out of this node, and that lets us write an equation at that node VA. There are no other nodes on the circuit, just the reference node and node VA. Okay, so when I write that node voltage equation, I'll do that in green. Okay, I have this voltage is VA, and this voltage with respect to the reference is 1 volt. Okay, there's no voltage drop across a wire. Here's a voltage rise of 1 volt. This is at 1 volt. Okay, so this current, I'll call this I1. I1 would be VA minus 1 divided by R1. So this is node VA equations. All right, and then I add to that VA, and I divide by, I'm getting current I2. So the current I2 is VA minus 0. This volt, you find the voltage across the element, it's VA minus 0, and you divide by the impedance, 1 over CS. Okay, and then finally this current coming this way, it goes through two elements in series. So the voltage drop across the two elements, here's plus VA, and this point is 0. So it would be VA minus 0 divided by that branch impedance. So that would be LS plus R2 equals 0. Okay. So there's the equation for VA, and then I just need to relate VA back to V out. Okay, and so I can do that because I can easily calculate this current. I call it I2 here. V out would be I2 times R2, and we already found what I2 is in terms of VA. Okay, so that would be VA minus 0 divided by LS plus R2. Okay, so that's the equations. All right, we have two equations, two unknowns. All right, we can actually use this first equation to solve for VA and then substitute that back into the second equation. But I'm going to use Matlab to do that, so I'm going to, switch over to Matlab at this point. Okay, so jumping into the Matlab, here are the symbolic variables that we need. So you type sims and you list the symbolic variables, and then basically just type in the equations. I like, as you know, to label the equations, equation 1, and the equal sign of the equation needs a double equal sign in Matlab. Okay, so equation 1 for VA, equation 2 is relating the output, and so we'd already talked about that earlier in the video. So you use the symbolic toolbox to solve for equation 1 and 2, equation 1 and equation 2 for V0 and VA, and that puts the answer in a data structure. So you can pull the output back out. Vout is s dot vout, and I went ahead and collected all the terms as a function of s. All right, so you get a little bit of a cleaner look for the transfer function. So this is the transfer function because it's Vout over Vn. Remember, we set Vn to be the impulse. Okay, and so this is actually the Laplace transform of the impulse response, which is the same thing as the transfer function. Okay, I collected on the variable s, and so you can see it's a ratio of polynomials just like we expected. Okay, so hopefully you can appreciate the power of this technique, especially if you use Matlab to crank through the nasty algebra. All right, so that gives us a model for a circuit.